Hello, everyone. This time we are going to talk about section 6.2. Let me turn to the PDF file. Okay, 6.2 is a homogeneous linear equation with constant coefficient. As I said before, chapter 6 is an extension of chapter 4. So the concepts are very similar. So here we consider homogeneous. Homogeneous means the right-hand side equal to 0. Let me activate some laser point. Okay, laser point. Where is the laser point? Oh, here. Okay, so homogeneous means the right-hand side is 0. And you can say this is a linear nth order equation. All the coefficient here, an minus 1, dot, 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 to a1, a0 are all real constant, as we discussed in previous section, if you can find n linearly independent solution to this homogeneous equation 1, then you can express the general solution of our homogeneous equation 1 in the form just like equation 2 here. Basically, just a linear combination of these n's linearly independent solution. Very easy. So how do we find this n linearly independent solution? Now, let's recall in chapter 4, we assume the solution is y equal to e to the rx. Okay, so let's assume the solution is look like this. Then let's substitute this solution into the homogeneous equation number 1. Remember, before we like to use a differential operator to rewrite equation number 1 as equation number 4, Lyx equal to 0. And where Ly is an yn plus an minus 1 yn minus 1 plus dot 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 a1 y prime plus a0 y. And remember, what is L? L, well, in previous section, let me change to the previous section. This is important. Okay, let me show you. Okay, remember L, what is L? L is dn plus p1 dn minus 1 plus dot 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 pn operate on y. So here, we will use later so here we are going to use later is L equal to an dn plus an minus 1 dn minus 1 plus dot 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 plus a1d plus a0. Let me write down. Let me activate. So as I say, so L will be, oh, sorry. This pen is not easy to control. Let me erase this. Okay. Okay, let me write down L. Okay. So L is, let me activate this. So L will be like L equal an d power n plus am minus 1 d power n minus 1 plus dot 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 plus a1 d plus A0. Oh, so this is important. We will use that later. Okay. Okay. So let me just erase this. Let me erase this so we can continue. Okay. So next. So if we substitute, let me use the, okay. So if we substitute the solution, we assume the solution to be y equal to e to rx. So if we substitute y by erx, you will see this become, if you do the derivation and the differentiate that, you will find is equal to am r power n erx plus am minus 1 r power n minus 1 erx plus dot 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 plus a0 erx. Since all the terms had a common factor e to the rx, we can move it over the expression and it become erx times, in the parentheses you have a polynomial of r, an rm plus an minus 1 rm minus 1 plus dot 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 plus a0. We can call this polynomial of r to pr. So easy. So LERX will equal to ERX times PR, okay? We call this, remember, we want this equal to 0, right? So since ERX is always larger than 0, so the only way to make it 0 is this PR, this polynomial equal to 0. And this is exactly in chapter 4, we call it auxiliary equation or characteristic equation. Think of n equal to 2 cases. You will understand that very easily, okay? So the following will come to solving these equations. We have the following 3 situations as before. First, all the roots are distinctive real roots. For example, we have R1, R2, da da da, Rn is the root of the equation number 6, our auxiliary equation. They are all real and they are all distinct, means they are all different from each other. Then the n solution to the equation number 1 is y1x equal to e to the r1x, y2x e to the r2x, dot dot dot, ynx e to the rnx. So next thing you might ask, how do we know this n solution, they are linearly independent or linearly independent? Well, to prove this, we need to consider the linear combination of this n solution equal to 0. If you can only find all the coefficients C1, C2, dot, 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 Cn, they are only equal to 0, that means they are linearly independent solution. Well, the proof will be in the following. I'm going to skip that, but I recommend all of you to read the proof. Read the proof, that means from this, let me use the drawing, okay? I recommend to read the proof from here to here. So here the 14, okay? So we'll be started from basically starting from equation 8 to equation 14. This is a proof. I recommend you to read the proof. It's a very good proof, but I'm not going to spend time explain the details, okay? Also, remember let me erase this stuff, so we don't need this anymore. Remember in the previous sections, in the previous section, 6.1, at the last, we mentioned there are several function sets are linearly independent functions. Okay, let me move to the, okay, here, see? This set here, let me activate the laser point. See? E to the alpha 1x, e to the alpha 2x, e to the alpha nx, as far as all alphas are distinct constant, mean they are different from each other, then this form a linearly independent function set. So as you can see here, so as you can see from here, since our R1, R2, till Rn, they are all different. So these functions will be linearly independent, okay? So this is the case one, when the root of the auxiliary equations, are all real and distinct roots. And for the other two cases, we will talk about that in next video. Okay, so let me turn off this.